Improving Cooling System Efficiency, Part 8, Water Conservation Strategies. So we've talked about the relationship between makeup and cycles of concentration. And we've said that the cycles of concentration are regulated by the bleed. So let's take a look at the relationship between makeup and cycles of concentration. And here we have a graph that does just that. And you'll notice that as we operate a cooling tower at relatively low cycles, let's say here we have 2 cycles of concentration, our makeup rate might be 30 gallons per minute. As we increase cycles to 4, we have a dramatic drop in makeup demand. And as we continue that process of looking at higher cycles, we see that the makeup demand starts to fall off, but then tends to reach a point of diminishing returns where we're not really seeing a significant decrease. Although we are still increasing cycles, the return on that is not as great as we get when we're at the lower cycles. So the goal here is to achieve maximum cycles of concentration to minimize our makeup without running the risk of fouling the heat transfer surfaces in the condenser of the chiller or in the cooling tower fill. We want to optimize cycles to minimize water conservation, water consumption, and make that whole process as efficient as possible. So here we'll use an example of 4 cycles of concentration. We achieve a certain makeup requirement, and what would happen if we increase that to 10 cycles? If we were able to use a technology that would allow us to do that, we would see that we see a dramatic reduction in makeup requirement, that our water consumption would go down significantly. And we can calculate that. The impact on cooling tower makeup based on cycles, if using our 1,000-ton cooling tower example at 4 cycles, we calculated 43,200 gallons per day. If we had a way to operate at 10 cycles, we could reduce that to 36,000 gallons per day, which represents a 16.7% reduction in water consumption. Very significant improvement in overall water efficiency usage in the cooling tower. And just for comparison, let's say we were able to go up to 20 cycles, we would get some additional reduction, but you can see we only go down to 34,100 gallons per day. So the impact is not as great as we continue to increase the cycles of concentration. And there are some practical limitations for how high we can get cycles. All cooling towers require some bleed to remove the suspended solids in the water, so we can't operate at infinite cycles. We need to pick the most optimum cycle of concentration for the particular water quality and operating conditions at that particular site. What factors limit cycles of concentration? Well, as I mentioned previously, the evaporation effect at the cooling tower tends to concentrate mineral impurities, and if you over-concentrate some of those, you'll end up producing scale deposits in the system. These consist primarily of calcium salts, calcium carbonate, calcium sulfate, calcium phosphate in some cases. In some areas of the country, silica is a limiting factor. So we can't operate the cooling tower at cycles of concentration that exceed the solubility limits of these insoluble or sparingly soluble salts. Otherwise, we'll foul the system with mineral scale deposits, and that is, as we know, can rob us of efficiency, both energy and water efficiency. One tool that we have provided is a cycle of concentration estimator tool, which helps end users arrive at an estimate of what is a permissible cycle of concentration based on their makeup water quality. Cooling towers are largely operated within limits imposed by the water quality in that particular area. So if we can get an analysis of the makeup for calcium and magnesium hardness and alkalinity and sulfates, silica, the pH of the water, the specific conductance or conductivity of the water, these values are readily available by testing or from your vendor. And once we know these values, we can plug those into the cycle of concentration estimator tool, which is in your toolkit, and allow it to calculate a recommended cycle of concentration. So we've done just that. Here's the output of the cycle of concentration estimator tool. We've taken that water data, plugged it into the tool, and we come up with a recommendation of maximum cycles based on calcium carbonate of 3.4, calcium sulfate 20.5, or silica 68.2. So we picked the lowest number, which is the limit on cycles based on that impurity, and in this case it's 3.4. So our maximum recommended cycle is 3.4 based on that water quality. That is for a traditional water treatment program. So how does this all fit together with regard to water conservation? Well, we said that cycles of concentration are determined by the ratio of the impurities in the cooling tower water to the same impurities in the makeup. And we regulate these cycles based using cooling tower bleed. So increasing tower bleed or blow down to drain decreases cycles. Decreasing the bleed allows the cycles to increase. And our goal ultimately is to operate at maximum cycles of concentration without causing scale deposition. This minimizes freshwater makeup demand and reduces blow down to drain.